All right, let's look at one more example. This one is much more complicated. There's a bit more going on, but we should still be able to use the same type of process and workflow to do process of elimination and arrive at a final answer. So at the top here is the carbon-13 NMR, and each of these peaks is additionally labeled with depth NMR. This depth NMR then tells us whether these carbons that are responsible for these signals are themselves carbons with no hydrogens, 1, 2, 3, or 4 hydrogens attached. The middle here is the proton NMR, and down at the bottom here there's a mass spectrum, and actually some fragmentation is given to us. And finally down here is just the most important peaks in the IR spectrum are given to us. So we'll go through and do the exact same business. A challenge with this one is that the mass spec has a molecular ion that's very large, so this is a 330 m over z. There's m plus 2 out here, and m plus 4. So we should expect to see 2, at least, different kind of halogens or sulfur that's involved in the formula. And another weird thing about this data is that they didn't really give us relative abundance or intensity information, so it's a little bit hard to calculate exactly what's going on. However, we should look at the fragmentation and see what we can infer. So we have some fragmentation here. So one of the smaller fragments, it has a 1-to-1 ratio of its isotope, so 294 to 296. That means that this fragment has bromine in it. Another fragment that's smaller is 224 and 226 AMU signals in a 3-to-1 ratio, so that fragment must have chlorine in it. Finally, there's a third fragment here that's also expressing a 3-to-1 ratio. That tells me that that fragment also has chlorine. So together, all of this tells me that at a very minimum, our molecule has 1 bromine and 1 chlorine. I don't know whether there's 2 chlorines or not. I only can say that there's 1 for now. I only can say that there's 1 because I don't know whether the fragments that are being shown here are coming from kind of 2 different types of fragmenting into 2 different sizes of fragments, or if it's actually from like 2 halves of the molecule, each containing 1 chlorine in it. So our m plus 1 signal intensity here might be a little hard to use to figure out a number of carbons. So why don't we go through and first just use our carbon NMR to determine the minimum number of carbons that we should have in this molecule. So if I go through and count, there's 1, 2, there's 6 total here, so that's 8. Ignore chloroform. Here's 9. Looks like this is indicated to be 3 here, so that's 12, 13 carbon signals at a minimum. So in the NMR, we have 13 carbons at a minimum. In the proton NMR, we can use the integration then to figure out our minimum number of hydrogens. So if we assume that our smallest integration size here is 1, then we have 1, 2, 3, 4, each of those being kind of a 1, 1, 1, 1. The signal here at 3.5 ppm looks like it's twice as big, as does the one at 2.6-ish ppm, as does the one at 2 ppm. And then finally, the signal at less than 2 ppm appears to be rather large here, right? If you go through and take a ruler to this, this looks like 1, 2, maybe 3 times even larger. So it's kind of looking like 6 hydrogens here. That then gives us a total of 16 hydrogens that we should think about as a minimum number. Right? So let's go through and check our chemical formula and see if we're missing anything at all. Now let's go to our IR and see if we can get any more information about functional groups before we move on to figure out an actual chemical formula. So in the IR, this says there's a strong signal at 1705 wave numbers, and another strong signal at 1683 wave numbers, and then a medium signal at 1604. So for me, that makes me think that there are 2 signals in the carbonyl region and 1 signal in the alkene region. So I have 2x carbonyls, 1x signal for alkene, all kind of coming from this right here. The thing we always want to be careful about with alkenes is that there could be multiple alkenes, but they will often just show up in the same region, especially when it's a benzene ring, right? So we don't want this to mean that there's only 2 carbons that are engaged in an alkene, right? It's just that there is an alkene signal present, and that there's 2 different carbonyl signals present. So based off of this information, then my chemical formula could be a little bit more narrowed down to be 13 carbons, 16 hydrogens, at least 2 oxygens, and then bromine, chlorine, and maybe anything else. So let's go through and write that out. So our first pass at a chemical formula will be C13H16 BrClO2. And so if I go through and figure out what the total mass I've accounted for here is, the calculator tells me that that's 318 AMU. That is not enough to match our molecular ion. I'm off by 12. And whenever in mass spec you're off by a convenient number like 12, then you probably should just assign that to being an extra carbon, right? So then I would modify my formula to be C14H16 BrClO2. The reason I feel comfortable doing that is that actually in the proton NMR, there is this very large signal for 6 hydrogens. There's no way for one carbon to have 6 hydrogens on it. So this is almost certainly coming from a set of carbons and their hydrogens, right? So there's got to be some symmetry in this molecule, which then means that definitely there is at least one signal in the carbon NMR that's showing up at the same location as another one, which means that I counted 13 signals, but I don't actually have 13 carbons. Again, there was some symmetry indicating I should have a little bit more. It looks like I actually had just one more than I expected. Given this nice formula, let's get to our DOUs. 2 times 14 plus 2 minus 16 minus 2 for the bromine and chlorine divided by 2. That's equal to 6. So from here now we have enough information to try to deduce a little bit more. Let's go see what other type of functional group information that we might have missed out on. So we definitely had carbonyls. Actually, if I look at my proton NMR, it looks like I have this signal near 10 ppm. We should have an aldehyde. Right? If I look at my carbon NMR, I have 2 signals showing up in the carbonyl region, both closer to 200 than they are to 160. That makes me think ketone and aldehyde, or ketone or aldehyde. Secondly, the depth NMR information here is a little bit small to see, but the left signal is positive for the depth 135 and the depth 90. And the right signal has no peak, so just no signal for the depth 135 and depth 90. So that's the case for all of these. It's depth 135 in the top row, depth 90 in the bottom row. What that tells me is that these 2 carbonyls are not the same, right? They're not both ketones and they're not both aldehydes. So an aldehyde carbonyl has a carbon that has a hydrogen attached. This is exactly a CH. And in a CH situation, for the depth NMR, you would expect positive signals in all of the depth experiments. So I can assign the left signal here to being the aldehyde. In order to have a carbonyl that has no hydrogens attached, yet is showing up in the ketone or aldehyde region, well, the only other possibility is a ketone, right? So this all suggests that I have a ketone and an aldehyde in my molecule. I should go back and check that that makes sense with the IR. Looks like it does. I have a stretching at 1705 wave numbers and a stretching at 1683 wave numbers. Both of these values are a little bit lower than you would expect for the ketone or aldehyde respectively, which should then make me think about whether or not there's any conjugation that's affecting those stretching frequencies. Okay, let's see what other information we can learn from the carbon NMR. In this kind of 100 to 160 ppm region, I have 6 signals. This is generally the alkene and aromatic ring region, and just the fact that I have 6 signals is very strongly suggestive of a benzene ring. Not just a benzene ring, but a benzene ring that is not symmetric, such that all of its 6 carbons are giving different signals. The depth NMR tells me that 3 of those carbons have no hydrogens attached, and 3 of them do have hydrogens attached. So that means I need to have some pattern. I'm just going to put 3 groups on here for now like this. But I have some pattern of attaching 3 groups to this one benzene ring, right? And leaving the other 3 carbons as just CHs. And once you draw a benzene ring as a potential piece of your molecule, that just accounts for so much degrees of unsaturation that we should just go through and just double check how many of those we have already. Benzene ring is 4, ketone is 1, aldehyde is 1, that's a total of 6. We're already taking care of all 6 of our degrees of unsaturation. right? So everything else in this molecule, not going to be a ring, not going to be a pi bond. If I kind of go through and look here, it looks like I have something that's pretty downfield. So this is close to 70 ppm in the carbon NMR. It's a no peak, no peak, which means that it's a carbon with no hydrogens attached for some reason, right? And that, again, this is going to be a downfield one, right? Just the fact that this signal is kind of so separated from the other ones tells me there should be something unique that I can point to explain why this signal is showing up here. And then finally, I have all these signals in kind of the alkane or alkyl region, kind of the 20-ish to 30-ish. None of them is closer to 15, so there's not like an isolated methyl group at the end of a carbon chain. So if I have a methyl group, it's probably going to be close to some sort of de-shielding effect. Now let's look at the splitting patterns in the proton NMR to see what other kind of fine-tuned information we can gain about the way that these carbon atoms are arranged. So the aromatic region here, if we kind of qualitatively look at the splitting patterns here, these are much smaller J values than what you see in the upfield region. In general, the upfield region is going to have just regular normal J equals about 7 Hertz. So just looking at this tells me that these are very small J values. If these are all going to give small J values, that means that none of these hydrogens have a neighbor that is kind of a 3J coupling distance away. The only way to achieve that around a benzene ring is to put those three groups then kind of equally spaced out like this. Right? So that means that all of these hydrogens are going to have 4 J couplings. And in fact, if these three groups are different, then I should have 4 J couplings that are different from each side. So I should have a doublet of doublets, or perhaps just a triplet if those J values are identical. If I go through, you can kind of see that showing up in here, right, in the zoomed version. So you can kind of see that triplet, triplet, triplet type of a pattern. So then this substitution around the benzene ring makes sense. In the upfield region here, I can see that I have a triplet at 3.5 ppm. I have another triplet around 2.6 ppm, and then at 2.1 ppm that looks like a pentet, and finally the singlet for the 6 hydrogens. The 6 hydrogens here being a multiple of 3 is strongly indicative of a methyl group, and here would be 2 methyl groups. And the fact that they're singlet means that they're isolated from everything else. The triplet, triplet, and pentet pattern here, we kind of want to go through and figure out what type of attachment that looks like. Best way to start is to start with the fact that we have a CH2. Let's say it's a CH2 and it's the most downfield one. So let's say it's attached to something that makes it downfield. Call it the electronegative atom. It's got to have 2 hydrogens on it. It has a signal that's a triplet because it is attached to another carbon with 2 hydrogens on it. In order for us to achieve a signal that's a pentet, this needs to be a pair of hydrogens, because the integration is 2, but a pair of hydrogens that themselves have 4 neighbors. Right? So kind of just by the way that I assigned all this, I can't have those be the pentet. I can have these be the pentet if I add 2 more neighboring carbons to the right, such that I can say that this is the case. And finally, that then leaves me with those hydrogens being those right there. And that would necessitate that whatever's out here is kind of not attached to anything CH. Right? So it's attached to a carbon or an electronegative atom, but not a CH containing group. So again, I was able to use a splitting pattern to figure out that I had a 3 carbon chain because I saw there was a triplet for one end of that chain, triplet for the other end of that chain, and a pentet for the middle. So at this stage, we actually have all of our pieces. It looks like we have an aldehyde, we have a ketone, we have a benzene ring, we have a 3 carbon chain with an electronegative atom on it, and then we have to have 2 methyl groups. So from here, we definitely are trying to do a little bit just more fine-tuning. We have to figure out how to put everything around here. So going back to the IR, I had made a comment that these stretching frequencies are lower than we expect, and that's likely because of conjugation. Well, we have our benzene ring, so almost certainly we should be putting both our aldehyde and our ketone around this benzene ring as groups. I'm doing that because both of the stretching frequencies for the carbonyls are lower than expected, likely both conjugated. So why don't I go ahead and do that? So why don't I expand my workspace here so just I have a little bit more room to work with. So I want my benzene ring. I'm going to arbitrarily put one group on top here. So let's say that's where the aldehyde is. And let's say that this is where the ketone is. Something important to keep in mind is that I haven't decided at all what's on the other side of that ketone, and I still don't know what's over here. Right? Those are the two pieces to keep track of. Going back to my other pieces now, so I've taken care of aldehyde and benzene ring. Now I need to figure out what's going on here. So for the electronegative atom that is causing the downfield shift of this triplet here, my choices would be either chlorine or bromine. Right? So why don't I stick that here as my choices? If that's the case, then this is the end of the line, right? This is the end of the chain. So this side of the chain has to be attached to something. This can be either attached directly to a benzene ring or attached at this ketone position. Those are my two possibilities here. So the hard part at this stage is to figure out which one of those is the case, right? And so for looking at the chemical shift here, we should see that this chemical shift is coming in at 2.6 ppm versus kind of the typical chemical shift when you're adjacent to a carbonyl of about 2.1-ish ppm. And so for that reason, I'm inclined to put this chain as the group attached to the benzene ring. Again, that's a little bit more subtle and requires you to do a little bit more comparison to other known data sets. But again, this chemical shift here for this purple pair of hydrogens is a little bit more downfield than I would expect for just being at a position next to the carbonyl. That's why I put it on the benzene ring. So I would do that, 1, 2, 3. So I'm still going to leave this as Z just because I didn't know if it was the chlorine or the bromine yet. I should go through and just see what I'm missing now. It looks like I'm missing just the two methyl groups and a chlorine or a bromine. These two methyl groups are showing up close to 2 ppm, so perhaps it makes sense to attach them right here. Really, that's the only other place I could attach them to because there's no other attachment points here. This carbon cannot be a CH, and I know that because I've already accounted for all the hydrogen signals that I have in my NMR, and I actually only needed one more attachment point to put on the remaining halogen. Right? So I'm going to just indicate that here quickly as a squiggle, and then put a Z. From here, then the last thing to do is to try to figure out which halogen should be assigned to which position. So our difference is going to be that if we had a chlorine here, chlorine's more electronegative, we would expect a downfield shift of this hydrogen and its carbon. If we had the chlorine here, we would expect the more downfield shift for this carbon. And looking at this data, what I see is that there's this cluster of peaks out here that are all kind of very similar in chemical shift, and there's this one lone signal that is way out downfield. This lone signal, again, we had started earlier as being a depth no peak for both depth 135 and depth 90, suggesting that it has no other hydrogens attached to that carbon. And so that's got to be this carbon right here that I will star for us. And if it's that carbon and it's the most downfield, I guess my little bit of a circumstantial argument is that it's better for me to put the chlorine here, because if I put the chlorine on the other CH2 here, I would expect a signal that's maybe a little bit further shifted away from the rest. Whereas with bromine is not that electronegative. It doesn't cause as much of a downfield shift, meaning that I would expect this CH2 and this CH2 to show up in a similar place in the carbon-13 NMR. So again, that's a bit of an inference, but it makes me think that this is the chlorine and this is the bromine. Overall, getting us to a final answer of a benzaldehyde with a ketone and a bromopropyl chain attached. Turns out that this is actually the molecule that this data is taken from. So obviously I knew that before presenting this to you, but it is a pretty reasonable expectation that with a little bit of work, trial and error, guess and check, and a lot of discussion, you're able to turn this information into this structure. So that was a nice range of examples of unknown structure determination, ranging from easy to medium to hard. Um, in practice, this type of a process is very important for chemists. So you can imagine, let's say that we discover that some sort of a plant is giving us really nice medical benefits. We need to figure out what the structure of the molecule that gives those medical benefits are so that we can actually use that to kind of further develop medicine. Well, you have to extract the active ingredient. From the active ingredient, then you take NMRs, IRs, mass specs, and from that you can infer structure. In other situations, such as when I perform a chemical reaction, I know what the two pieces I'm mixing are, and that helps a lot because if I mix those two pieces together, those two reactants together, I should expect at least some structural attributes of those reactants to remain in the products. And so even though the daily process I go through is a lot of unknown structure determination, it's much easier than the process that was shown here because I'm starting with so much more structural basis. Both of these situations at the end of the day still require you to know and understand all of the bases of spectroscopy and how to apply them to use process of elimination to get to the structure that best explains the spectroscopic data.